Hello and welcome. You can use test steps for analyzing closed processes. But before uh, going over this video, please make sure that you know how to evaluate properties of closed systems. Okay, so let's go and take a look at what we mean by a closed process. A system is closed and it is unsteady. Also, an important assumption is that it goes from a beginning state to a final state. In other words, you can integrate all the equations and simplify them into algebraic equation. Closed processes are covered in chapter 5. The foundation is laid out in chapter 5, and all the other chapters have different kind of applications, 7, 11, 12, 13, and 14 of closed processes. Okay, so let's go over a few quick examples. I've already started a bunch of animations, so I'll quickly browse through them. This one shows how the governing equation simplifies. Again, starting with the very general governing equations, mass, energy, and entropy. For a closed process, the transport terms drops out, and the differential terms on the left-hand side, multiplying by dt on both sides, we can then integrate them because we know the system goes from a beginning state to a final state, and thereby we are obtaining the final equations, which are algebraic. So change in energy, change in entropy are given by, on the right hand side, heat transfer and work transfer here, and entropy transfer by heat and entropy generation. So this is a very simple equation compared to the generic governing equations. As practical examples, here it shows a block of solid cooling down, starting from a beginning state to a final state, as you can see. Clearly an example of a closed process. Using the SL model probably will solve the problem. Here is another example of a constant volume heating process. The gas is being heated at constant volume. As you can see from the PV diagram, the volume remains constant. Again, it goes from a beginning state to a final state. Here is another example of a constant pressure process. The piston moves up and the pressure remains constant. If you do a free body diagram of the piston, you can prove that. And again, the TS diagram and the PV diagram shows the process. Here is another example. In this example, actually a bunch of examples. This is an isentropic expansion. Entropy remains constant here. You can also see how the isothermal expansion or isobaric expansion, where pressure remains constant. With the same piston cylinder device, all these different kind of processes can be carried out. This is a composite process. Notice that it starts with a constant volume process, then it moves into a constant pressure process. But in all these examples, you notice that the system is uniform. That's why these are called simple process or uniform process. On the other hand, a process could be also, look at the red boundary, the process could be made of a system, a composite system, where there are subsystems A and B, and in this case it's a mixing process where two gases may be mixing together from a composite beginning state described by BA and BB states to a final state. There need not be mixing. For instance, if we put two solids, one hot and one cold together, and again the red boundary is our closed system. As you can see, there could be internal heat transfer, and the system goes from BA and BB states to a final state where the equilibrium is reached. So let's take a quick look at the test steps used for solving such problems. So if we go trace the road to system analysis, closed systems, closed unsteady processes, and generic branch, the simple process is what most of the examples have just gone through. And based on what is the working fluid, working substance, you can, for the solid heating or cooling problem, it will be the SL model. And for example, if we go with the gas model, suppose if as soon as you come to this page, the default page is again always hands-on example. So there are details example of closed process solutions here. But just to give you an overall idea, so here is our closed system state panel. If you recall, we have covered that. Suppose you have air at 100 kPa. If you recall, we solved a problem such as this to find the state of a gas. If you know the volume, temperature, and pressure, state is calculated. Suppose this is our beginning state. We started with some air at this state, and suppose at constant pressure we heated such that the volume triple, and of course the mass doesn't change, so we will make sure the mass remains constant. Now the temperature is calculated, so the beginning and final states are known in this problem. We can go, of course the graphics panel will show that if you draw a constant pressure line, it should pass through both this state 1 and 2. In the process panel, notice this is the addition here. It shows the beginning state and final state through a diagram, and you can load the beginning state as state 1. Immediately air is shown as the working fluid, and state 2 as the final state. And what is known here? Well, let's see what the calculator can do for us. The moment we click calculate, you notice that it can calculate all the variables because the energy and energy equation supplies all the other variables that is needed for this solution of this problem. So therefore, the heat transfer is calculated, the boundary work is calculated, and a supercalculator can produce a detailed solution report as well as test codes. But that's for another video. Just to give you an idea about, instead of a simple process, suppose we have a mixing process or a non-mixing process. Again, once you select your material, suppose again it is a perfect gas model, in that case this state panel will not change, but the process panel, you will notice that the beginning state is now composite state. There is a BA state and BB state, FA and FB state. So you have to you will play with 4 different states here. Again, the mass, energy, and entropy equations are a bit more complicated because you have to keep track of the subsystems. But again, once you go through an example, overall it is just like solving a closed process problem, except you keep track of 2 subsystems. Where do you find problems of this type? Of course, chapter 5. If you go to chapter 5, it will have all kinds of closed process problem. As a matter of fact, section 1 is all about uniform system. Section 2 is about mixing process. Section 3 is about non-mixing process, etc. So I'll stop here and let you explore what type of problems you can solve with these closed process apps.